we have already learned first law of thermodynamics in our previous lectures. In this particular chapter, we will we will talk about second law of thermodynamics, and which is essential for a process to happen. So in general, a process to happen, it should follow not only first law, it should follow both first and second laws. Okay, so this is also crucial thing to discuss. So in this chapter, we'll talk about second law of introduction of second law of thermodynamics. We'll talk few keywords we will be using frequently, such as thermal energy reservoirs. We'll talk about heat engines, and this second law basically will have two statements, Kelvin Planck and Clausius statements. We'll talk about. So this Kelvin Planck statement is in the context of heat engines, and Clausius statement is in the context of refrigeration. We'll talk about that. We will also learn about refrigerators and heat pumps, perpetual motion machines, Carnot cycle, thermodynamic temperature scale, Carnot heat engines, and refrigeration in this particular chapter. In the after this chapter has finishes, we'll talk about entropy, which is again a new property which will be arises because of this second law of thermodynamics. A new property arises. We need to look into this property. Next thing we are going to talk about is exergy, and then we can we are in a shape to learn proper gas cycles, gas steam cycles, gas cycle, vapor cycle, vapor cycles, proper on which real machines or real power plants used to work. So these things we will discuss after we will finish exergy and entropy. Okay, and then it may conclude our thermodynamics course. Okay, so still far more to go.
Sir.
Huh.
Sir, is this chapter included in the internal assessment on Thursday?
No, it won't be, although it comes in unit 1, but since we have covered unit 1 and unit 2 interchangeably, so whatever things I have covered till first law, we'll ask that.
Sir, one more question.
Okay.
Sir, can we expect the questions that you gave in the previous assignment, like those questions in the exam?
Similar questions you may expect.
Okay, sir.
Okay, so let's first talk about what exactly the second law of thermodynamics is. So before moving into the proper statement, what second law of thermodynamics talks about, we will take up one example. Like we have already seen this before, but to just give a preface of it, we are going to discuss it again. So let's suppose I have a hot coffee, and which is having at higher temperature, and atmosphere is having lower temperature. The heat flows from higher temperature to lower temperature spontaneously. Okay, you don't have to worry about, and heat will flow from higher temperature to lower temperature. That is the general tendency of whole universe. Everything thermodynamics, in thermodynamic sense, the higher temperature substance loses heat to lower side. Again, when we talk in terms of transferring heat to a paddled wheel, so when you rotate this your paddled wheel, there are some wheels around it. In a container, the fluid will heat up. Okay, but the opposite doesn't occur. It means when we try to heat this particular uh, paddle wheel, it doesn't rotate automatically. Okay. Similarly, your electrical wire dissipates when electrical energies flows in through this electrical wiring. It dissipates heat, but it doesn't happen that if you heat a electrical wire, your electricity generates. It doesn't happen spontaneously. Okay. So these things doesn't happen only because there is something called um, there is something second law of thermodynamics that comes into picture. Although first law of thermodynamics tells that your overall energy is conserved. Okay, so heat is also energy, and if I blindly follow first law of thermodynamics, then these two cases doesn't seem to be violated. Why? The same amount of heat when I'm giving, it should also be converted to the work, right? Because it is also a form of energy, but in reality it doesn't happen. Also here, the amount of heat that is being given to the electrical wire, it should generate some electrical energy out of it, right? But it doesn't happen. Or if you say so, the 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 heated coffee, the heat won't flow from lower temperature to higher temperature. Although the same amount of heat, I could argue that same amount of heat should be I mean, in some sense it is also conserved, but it doesn't happen. So for that, it has been concluded that there is something called not only quantity, but the for the process to happen, the quality of energy is also important
Sir,
for process to happen. Huh.
sir, sir, there are few of the participants who have joined the other thermodynamics meeting and they are not
No,
present
no,
in
no.
this meeting.
So yeah, please tell them to come here. I don't know how. You can message in your WhatsApp group or some group if you have. So on Monday, since Abhinay sir has also floated one MS Team invitation, so don't join that on Mondays. Be careful. Join my invitation only. When I mean in the invitation when which I have organized, you should join that 90 attendees. So you can WhatsApp them. So who is the class representative or anyone? You guys have any WhatsApp group, closed group? Please message them. Okay. So we should not only talk about the quantity, we should also, rather both, we should talk both uh, quantity and quality of energy is important for a process to happen from one direction to another direction. Okay. And in the next chapter, this actually in order to seek the quality of energy, another quantity called entropy, I will not discuss right now, but just keep in mind it actually this property arises due to the uh, need of measure of this quality of energy. We can think of another quantity called entropy, and then we can define our second law of thermodynamics is such that Wait. It states that, let me state that, because we didn't formally define the entropy yet, but let me, since I'm discussing second law of thermodynamics, I should state that, but we'll take up this thing in the new next chapter when we talk entropy in broader sense. But I should write this uh, thing once. The second law of thermodynamics states that the total entropy of isolated system can never decrease over time. So from things from happening from this to this or this to this, something is happening. Okay, some new quantity that is being described as entropy, and it should never decrease with process to happen. Okay. So we'll not go into details, just I've written this statement, and we'll take up this statement in more broader sense in whenever uh, we follow entropy in broader perspective. Okay. So in order to gain more about more insight about second law of thermodynamics, or the things to happen, uh, okay, before that there are two more things I wanted to uh, talk about. So there are three characteristics of the second law of thermodynamics. First, the quantity. It tells about the quantity. Sorry, quality. Quantity is also already seen in first law of thermodynamics. Uh, Quality of energy. Second, the direction of process to happen. And third, it determines the theoretical limit of any process. We'll talk about later in detail about what theoretical limits is, and based on that, few statements are made, Kelvin, Planck, and all Clausius statements. So we'll talk about uh, to gain more insight about these thermodynamic second law of thermodynamics. We should be aware of some sort of thermal energy reservoirs, and that is, these are the building blocks to understand more about the thermodynamic analysis that are happening in the process. In the second in the view of second law of thermodynamics, we need to know the thermal energy reservoirs. So reservoirs are defined as a hypothetical hypo sorry body or substance with a relatively large thermal energy capacity, thermal capacity that can supply or absorb finite amount of heat without undergoing temperature change. So what does it mean? So you have a hypothetical body no matter how much heat you provide to this particular substance, its temperature won't change. It means, what does it imply? It has very high CP values or specific heat. Remember specific heat? The amount of heat required to raise a unity amount of substance to unity temperature. So that is called specific heat. So higher the value of a specific heat of a substance, so higher the value of Q it will take without changing in temperature in some sense. So all these reservoirs, so reservoirs not only takes up heat, reservoir can give finite amount of heat as well in some sense without going into any temperature change. Okay, so this kind of reservoir is called uh, sink, and this kind of reservoirs are called source. Okay, so this is source and sinks. The very good example of sink is your atmosphere, your rivers, lakes, oceans. So what atmosphere does, I mean, we humans are having much activity, and due to this we have thermal energy that is being transferred to the atmosphere. But atmosphere temperature changes a little over time, very little, or no change in in some sense you can say. Or you have a power plant that is beside a river or an ocean, and all the thermal energy is being sucked in by this ocean without uh, further increase or further significant increase in the temperature. It stays the same. Okay, so it acts as a reservoir. Okay, so what reservoir? To some sense, sink reservoir or sink, also called sometimes sink. Whereas sources are also a type of thermal reservoirs which is having again CP values very high, specific heat are very high. These are used in as such as uh, boilers in your steam power plant. Although these are hypothetical bodies, it doesn't actually occur, but in some sense, yeah, they may be aligned towards kind of very high CP. Although these are hypothetically, ideally it is hypothetical, but yeah, it's there. So boilers, you have boilers, furnace in which the coals are being burnt and provides heat to the water to make it steam all the time. So usually these are estimated to be sources. Okay, or some sort of a reservoir which nothing ends. Okay, here ideally nothing ends. All the time you are providing heat, every time you are providing heat, and in sink every time you are taking up the heat without changing its temperature. Okay, so these are two examples, physical examples. Another example could be the phase change materials. Phase change materials. So what these phase change substances are? So they take infinite amount, almost very greater amount of heat, and even though temperature doesn't change, right? We have seen that during phase changes. We have seen the plots. We have seen few plots, right? We have seen few plots such as you have. We have seen that this, and this. So during this period, the temperature doesn't change, right? Even though the phase has been changed. So such subcooled liquid, saturated mixture, and superheated vapors, saturated states here. And between these two states, the temperature doesn't change. What happens? Even though I am supplying the heat, right? And we can see the temperature doesn't change. So see, this also acts as a thermal energy reservoirs in some sense. Okay, one more thing I want to talk about in this thermal energy reservoirs, that there is something called thermal pollution. So thermal pollution often occurs when your industry wastes are uh, in some sense without proper management. It gives away the thermal energy to the ocean, and it increases temperature of the ocean locally at some point, and the marine life and uh, maybe some uh, yes, marine or ecosystem disbalances, unbalances. Okay, so those kind of things are comes under thermal pollution, and so it is a duty of these power plants to manage your thermal waste in such a way that it should not affect your ocean or your river or a lake or atmosphere, so that it should uh, cost you your marine life, or your should cost you to disturb you your ecosystems. Okay, so those things should be in a managed way, and you should also know that actually. So uh, the this keyword I just have introduced so that you guys should know that there are something called thermal pollution, and we should actually in managed way we can actually uh, take care of this thermal pollution. So it's a matter of another course or another uh, subject to study, but not here in detail. Okay. So the next keyword we are going to talk about are the heat engines. Just to preface it, let me show you this again. This particular sketch that. Excuse me. Who is this? Who is this? Please mute yourself. Huh. Okay, so let's suppose I have a container that contains water, and we have a paddled wheel on it, and we do some work on this. We try to move, shaft work is happening on this water, and you can see that some amount of heat is being generated, or the thermal energy increases, and it happens spontaneously. So this thing happens, but the opposite is not always true. So when I heat up this water, and this uh, shaft will not rotate spontaneously. Okay, so this thing is obvious, and this is true also. But there are some devices, which can actually in some advantageous manner, it can actually convert some amount of heat into advantageous mechanical work. Okay, and those devices are called heat engines. And we'll see there are several devices that are there, and physically you can say your petrol engine, diesel engine, your vehicle, petrol engines. Not only this, steam power plants, your refrigerators, refrigeration cycles also comes under some sort of heat engines. Although the best fit example for the heat engine is the steam engine, petrol engine is basically this is basically closed system. So, and this is some sort of open system, you can say. We'll see why open, because you take the air and you mix it with fuel, you burn it, and you you leave behind the excess air or heated air outside to the environment. So in some sense uh, it is actually taking work out of it, but it's an open system, so it's not entirely comes under the heat engine. But steam power plants are closely related to the heat engines. So all sorts of devices are actually comes under this heat engine. So what is happening from high temperature source to low temperatures sink? So this is source, it takes away some amount of heat, and let's suppose this is your heat engine that is working in some cycle. It does some work, it throws away some heat. Okay, so this is how a typical uh, process of a heat engine. So a part of heat received by heat engine is converted to the work, while the rest is rejected to the sink. So this is how a process flows from uh, high temperature. It takes away some heat, uh, throw some heat in the low temperature sink or atmosphere, and in between intermediately it does some work. So we can see heat is actually generating some amount of work here, but in some clever way we are doing that. Not as spontaneously it won't do, but yes, in some clever way we can actually make work out of it. So there are some four characteristic of heat engines, such as they receive heat from higher temperature source, they convert part of heat to work, part of, okay, not totally, not 100%. And this is actually your Kelvin Planck statement that will tell that no machine can be made that all the heat should be taken up and produced to the work without leaving uh, anything towards the lower temperature sink. So that device we cannot make, and that violates our second law, and which is a proper statement that was made by uh, Kelvin Planck. We'll see. So it's a part of heat that converts into part of heat that converts to the work. They reject remaining waste heat to the lower temperature sink, and they operate on a cycle. So that is why I told that your petrol engine is not a proper heat engine. Basically this is some mechanical engine, uh, or yes, some mechanical form of cycle, but not purely heat engine. But yes, your steam power plant is a proper heat engine. Okay, and the fluid it is working on called working fluid. These heat engines, they work on some working fluids that are heated, put some waste heats outside, and it works in a cycle. So this is essentially called working fluid. It can be steam, it can be anything, it can be air fuel mixture or anything. Okay, this is a particular steam power plant uh, thermodynamic cycle that you are looking here. So it constitutes a pump, a boiler. Please mute yourself. Who is this? Rushikesh Bhatt. Okay, it has four essential components: pump, boiler, turbine, and condenser. So a steam power plant means it works on steam, and it is kind of power plant. It means it generates some work out of it, or finally through generator we can generate electricity. So okay, but so these four components: pump, boilers, turbine, condensers are there and steam goes in certain fashion. We'll actually talk more about in when we talk about vapor compressors compression cycles in a bit detail, but for the time being we should uh, know about how this heat engine works. Okay, so what happens? So you have a system boundary. Let's suppose this is your system boundary. And how does it operate? This your heat engine generally operates, takes some heat from furnace or from source. It it loses heat, and during that it takes out some work. So let's suppose this is your system boundary, and this is your heat engine that is here seated here, and this is the heat that is taken from Q in or QH or Q in is taken from the heat engine through the boiler. Okay, and it actually converts some work out from the turbine work out, and it releases some heat as from the condenser as Q out or Q lower out to the atmosphere, and it keeps on working on a cycle. Okay, so when to be more familiar with, we can actually draw this cycle on a TS scale, TS diagram. Uh, so we have a vapor dome. Since this is steam, we have a vapor dome. Okay, so let's suppose this is your one. This is your one. Let me go through once. Yes, this is your one. We should not be much concerned about what I am doing right now, but just be aware that these things we will learn in more details in the later section. So this is your one. So one is somewhere here. Okay, and from 1 to 2 we go somewhere like this, and this again goes from here to here. So this is your 2. Basically this is your 2. So 1 to 2 you are actually giving some work, small work. Actually this is your W in. Pump also required some work, so W in, and it goes from here to here until here till you reach 3. So 3 is here, and it takes away some amount of Q in to that to reach this state, superheated state. From 3 to 4 it is actually the turbine is an isentropic device, so isentropically you come down to this particular state called 4, and you come very right to from condenser. It is actually phase change device, so no change in temperature, so temperature remains constant. So this is, and you lose some heat. So this is how, and you get some work. So this is how your thermodynamic cycle works, but we will not care about right now much. Let me not concern more about on this, and we should be concerned more about the heat engines right now. We'll talk about in more details when we read this in the next chapter, next chapter probably. So yes, so we should be concerned only about right now, should be concerned about this. So workout, before workout we have turbine and pump also. So basically workout is nothing but actual out minus W in by pump. So this is the net, sorry, this is the net work that is being done by this heat engine, and this is the Q in and this is your Q out. And since so can we apply first law of thermodynamics here? First law. Tell somebody, tell me. delta Q plus delta U is equal to delta W. Okay. Since this is a cyclic process, so we are going from one place to do follow something, and we are coming at same place, right? So in one cycle, your change in internal energy is basically zero because we are reaching at the same state cyclic in one cycle. Okay, so change in so or not change in your Q, basically Q, total Q amount of heat that is being gained by this particular heat engine is basically your workout. Okay, so this is what we can actually apply. So here in this heat engine, we can actually write my work net out is nothing but Q in. Q in what exactly? So Q in minus Q out. This is what we can write through the first law of thermodynamics, right? So can we write thermal efficiency here? Yes, we can write. We can write thermal efficiency of any heat engine as my net. Maybe I have a slide for that. Yes, I have a slide for that. So thermal efficiency can be written as net work output divided by total heat input. So net work output is your W net out divided by total heat input is Q in, that is coming from furnace. That's it. And W net out can again be written in terms of, since it follows first law of thermodynamics, this is a system boundary, in and out, everything is conserved. We can write is Q in minus Q out by Q in, which can again be written as 1 minus Q out by Q in. So you can see that Q out is lower than Q in, right? So it cannot reach totally 100%. Yes, it should be below some percentage, some 100%, right? So this is how the efficiency of any heat engine is defined. Okay, we'll take up this particular and we'll then stop this uh, conversation here. The second law of thermodynamics, Kelvin Planck statement, I've already told about that. We have already given a preface that it is impossible for any device that operates on a cycle to receive heat from single reservoir and produce the net amount of work. It means this kind of device is not possible, which takes away some heat, some amount of heat, and it does the work, total work, and it leaves no heat to the sink. So it is entirely not possible. So there are some patents that files still in research community that it is taking away this thing. And so basically, what is the efficiency for this particular heat engine? So efficiency is work out by Q in, and you can see that work net out is totally, it is converting 1/1. Efficiency is 100% if we talk about in percentage. So basically this statement in another way, it is talking about the 100% efficiency of an engine, and which is not true. 100% efficiency is not ideally it can be, but in reality it's not. Okay, so this is not even possible. So for a heat reservoir to run, you should have at least some amount of heat to be sinked. at least. Okay, and this is what Kelvin Planck statement of second law thermodynamics states. Okay, so with this I want to, I'll not go further. We'll take up refrigerator and heat pumps later. Okay, so far any doubt, anyone, what we have learned?
No, sir.
Okay, okay, good. So let me take the attendance. Okay, but then we can leave then.